Good morning, everybody. Good morning. How was the weekend? Yeah? I know some of them were good. I know some of them were bad. And on average, it all works out, right? Tomorrow is a very important day. Exam autopsy. Don't miss it. Okay? No matter how well or bad you think you did. Because tomorrow's the day to fix it. For whatever fix it means, right? And I'll explain everything tomorrow when you come. But if you have to miss tomorrow, I need to know about it, right? So that we can make sure that you get the credit you deserve. We are moving forward with chapter 24. And I should finish chapter 24 today. That's the goal. And whereas last time we spent a lot of time with pictures and ideas about electric potential, today's the math day. There's just going to be a ton of math, ton of calculus. But don't worry, this will be the last calculus you're going to see for at least 3 chapters. Okay? And then, so because we're moving into applying voltage and current and resistance and circuits, and that becomes a big algebra game. And but this will be the last of the calculus for a little bit, till we get back to magnetic fields. Okay? So, as a send-off, right, to calculus, let's start with some calculus. Back last Wednesday, pretty sure I showed you the master definition for the change in potential as it related to an electric field. And it went something like this, right? And the takeaway from this definition is that potential, electric potential, we always have to talk about a difference in electric potential between 2 points. 0 can be somewhat arbitrary, meaning that I can pick wherever it is, although we're going to limit your choices there here in a bit. But the delta will always remain the same regardless of where we put 0, which is why we often talk about differences. This integration here is really saying, okay, look, if I want to find 2 points in space and measure their potential, I have to know what the electric fields are doing, and I need to make sure I integrate along with what those electric fields are telling me to do, right? There's that dot product there. What do dot products always do to vectors? Squish them down, but they always sort of report how much of one point's in the same direction as the other. Because if they're perpendicular to each other, what's the dot product become? 0. So that's just basically just picking off, right? A direction that is going with the electric field. So if I had a point charge, right, we know what the electric field for a point charge looks like, right? It's that kind of like that bad hair day sort of situation where the field lines all come out and away from that. And I could draw a lot more, right? But we get the idea of what's going on here. And if I want like that point and this point, and I want to know the potential difference between them, then I'm going to basically just kind of, I want to integrate, right, and sort of pick off the parts of the fields that are pointing in those directions, and this integral will sort of work itself out. At least we're going to trust that it's going to work itself out, because no matter where we are, and maybe I'll just let's get rid of that point for just now. No matter where I am, my electric field here is pointing away. And if I integrate in that direction away from my point charge, right, my ds, my integral direction, will all be consistent. And that makes sort of the inside of this integral fairly straightforward. I mean, basically this integral becomes a delta v equals negative. And then I've got to have 2 points here, more on that in a second, right? Becomes E times dr. What happened to my ds? What direction am I integrating along here? If the electric field is a bad hair day moving outwards, which way am I going to integrate? Outwards, right? And that is the away direction, which would be the dr direction, right? S being generic for any direction, R being specific for that away from direction, right? All right, so that's fine. Do we know what the electric field is of a point charge? Yeah. The electric field is KQ over R squared, isn't it? Magnitude-wise. And these are magnitudes now, right? Vectors are gone. Dot product, done. We have just magnitudes now, right? So I throw that into my integral here. KQ over R squared dr. And what's constant in that integral? K and Q. Okay. And then I have 1 over R squared dr. And we know what the integral of 1 over R squared dr is, don't we? Okay, so we can work that out. But what about the limits? Like again, we're trying to find a potential difference between 2 points. Okay? We can't, it's kind of weird. I want to find the potential at point A, but the only way I can reference what that potential is to compare it with another point somewhere else. So either I pick a different point in space as like a reference point, or we adopt a common reference point that everybody uses all the time. We're going to pick option B, because what we've standardized on in all of physics and electrical engineering and everything else is that the potential, by definition, V is equal to 0 at infinity. So a point charge, knowing what the potential is around a point charge, is I've got a point in space near that point charge, and that potential will be at reference with 0. And where is 0? Infinitely far away, wherever that is. Okay? So that means that my integral is going to go from wherever I am, point A, and it's going to head out to infinity. Point A is at a distance r from my point charge. And so I go and I do this integration here. What's integral 1 over r squared? It's negative 1 over r, isn't it? So a little bit worried there because natural logs were starting to crop up in my brain, and I was like, no, not natural logs. So it's going from infinity, from point A, I'll just call it r now. And that's equal to negative k, that's equal to positive kq. And then I get 1 over infinity minus 1 over r. What's 1 over infinity? That's 0. Okay? And I end up with negative kq over r. So a change in potential as reference to infinity, right, is negative kq over r. So we say that the potential of a point charge is kq over r. Now notice I dropped the negative sign and the delta there, right? Okay. This would be a change, right? Because we're comparing infinity with where we are. The potential is a scalar amount. And we set the value for high or low potential based on the sign of the charge, right? Positive charges are associated with high potentials. Negative charges are associated with valleys or low potentials. Positive and negative will be determined by the charge itself. And so even though we did this comparison with infinity, it's just like MGH or MGY, right? A change in potential energy is always different. You're always saying, well, what's the potential energy right here? Well, it depends on where you put 0. In gravitation, we let you pick 0 to make the deltas be easy to calculate. Here we're doing something similar, only the 0 is picked for you. It's picked at infinity, which I know you're uncomfortable. You're like, well, how far away is infinity? And the answer is, well, it depends. Okay? For an electron, it's not that far away. Okay? Have we done this exercise yet? If this table is charged, say, positively, and I'm charged negatively, how far away am I from this table as far as Coulomb's law is concerned? I'm infinitely far away. Why? Am I feeling any significant pull because this is positively charged and I'm negatively charged? Well, no, it depends on the amount of charge, right? If there's a gigacoulomb of positive charge over here, and I've got a gigacoulomb of negative charge, now I will feel a significant amount, right? Notice the distance didn't change. It was the amount of charge that determined whether or not it was a significant thing, right? So we'll play fast and loose with infinity. Infinity is going to be really convenient. What happens at infinity? I don't know, but field line's in there. V is 0 there, okay? It's a nice sort of, it's ground, right? It's like garbage collection, okay? Throw your garbage to infinity, it'll go away, right? So the potential of a point charge is kq over r. All right, what are the dangers of this equation? What does it look like? How close to the electric field equation is it? 1r, right? How easy is it going to be to write kq over r squared instead of kq over r? But Mr. Balogh, I didn't mean to. I can't save you there, right? Because kq over r squared is an electric field of a point charge, right? kq over r is the potential of a point charge. Very different ideas, very closely related equations, right? I'm sorry, it's just the way the universe is put together as far as we understand it. This is anywhere around that thing, right? So like, if I came in and wanted to know the potential right there, what would it be? kq over that radius, right? That distance, and right here, right? And if I wanted to know the difference between these 2 points, I could use that equation right here to find the potential there, and find the potential there, and then take the difference between them, because they're both referenced to a common value. What if I have more than one point? What if I've got multiple point charges? We're going to do the line here in a second, okay? But what if I had, I don't know, a situation where I've got a charge right here, charge right here, charge right here, and I want to find the potential, I don't know, right there. How do I find the total potential at point P? How would you do it if it were an electric field? Find each vector and its components and add the vectors together? Well, guess what? There's no vectors. So what are you going to find at P? You're going to find the potential of the first charge, the potential of the second charge, the potential of the third charge. And then what do you do at point P? Just add them together. And are there any components to deal with? No. So if 1 is a negative charge and 2 and 3 are positive charges, mind the sign. Notice there's no like absolute value signs on that charge. If it's negative charge, you put in a negative value to get a negative potential, right? But if I find the potential, and of course, you'll need to know the distances to point P. But if you find that V1 is equal to negative 3, and V2 is equal to 4, and V3 is equal to 6, well, then what's the potential at point P? 7. And there's no vector components. There's no directions to worry about, right? We just mind the sign and away we go. This is why potential is such a powerful tool, right? Is that it frees us from having to think directly about the electric field. We can measure the potential, and then at the end of today's lecture, I will show you how to get back to electric. We're going to reverse engineer that integral and see what happens. Okay, so let's do a line of charge. So here we go. We've done this before. We've integrated to find the amount of charge on a line, on a disk, on a ring, on a sphere, on a cylinder. We've done integrals to find the electric field of a line, of a disk, of a cylinder, of a sphere. Now we're going to do it with potential. Same process. It's the same process. What do we want? You're supposed to chant now. Potential. How do we get it? Integrate. All right. We're going to integrate what? A little piece of potential. Warning, warning, warning. That is not a volume. Right? We are finding electric potential here. Okay? What are we finding electric potential of? A line of charge. Well, okay, let's set up something so we know what our line of charge is here. I'm going to do a line of positive charge. This is like a rod, conductor maybe, something, okay? It's got positive Q all over it. And we are going to find the potential right there at point P. Okay, so this will be the potential at point P. In order to figure out what my little piece of potential, so this rod consists of a bunch of point charges all in a line. Okay, so that means I know what my little piece of potential is going to be, right? It's going to be K, and it's not a piece of K, it's not a piece of R, it's a piece of charge, right? Where'd the 1 over R come from? We just found it, right? Okay. I break the rod up into a bunch of little point charges, right? So that's what I'm going to do there. So the challenge is now to figure out what dq is. What's dq? It's a little piece of charge, but mathematically we can use linear charge density. This isn't, I mean, the only thing that's new on the screen is it's 1 over r instead of 1 over r squared. The process is the same. So, okay, so what's my integral look like now? Integral k lambda dx all over r. Now I've got to go find my r vector. So r vector, that means I pick some, I don't know, little piece, a little point charge that's sitting on my rod right here. Where does r start? R vector, where does it start?
0.
Nope. It starts on that point. It starts on that point charge, right? R points from the thing that causes and ends at the location where you're trying to find the thing that you're looking for. So R goes from there to there. That's R, right? How far away is R from the origin along the x-axis? X. Right? Okay. And how far is it along from the y-axis? I don't know, y. Okay. So that means that r is equal to negative x I hat plus y j hat. Oh, Mr. Bailey wrote an r vector. Well, that's because I'm used to writing r vectors. Right? Do you necessarily really need to know the directions? No. What we need is magnitude, right? We need to know how long r is. So how long is r? Yeah, Pythagorean theorem, right? Okay. It's just because I'm so used to looking at r vectors, it's sometimes, for me, feels comfortable to write it down, even though I only need its magnitude. Okay, so I've got its magnitude, integral k lambda dx all over square root of x squared plus y squared. Is my integral happy? No, my integral is not happy because I've missed something. What did I miss? The limits, right? So where does my rod start?
0.
At 0. Where does it go? However long it is. We'll just call it L. Okay? So this thing goes out to L. Okay. Let's see. Are there constants in this integral? K and lambda. I got dx all over the square root of x squared plus y squared. Okay. I think I made Wolfram Alpha do this one for me. Because I didn't want to think about it. Because, I mean, there's going to be a natural log, right? 1 over r drs tend to be, like 1 over x dx tends to have natural logs in it, right? So I think I just asked it. So it turns out that this integral right here, according to Wolfram Alpha, is equal to the natural log of x plus the square root of x squared plus y squared. Wolfram alpha. Okay, now we know who to blame. So what does that mean for my voltage at point P? It's going to be K lambda times the natural log of x plus the square root of x squared plus y squared. Y in this case just being a constant, it's, whatever distance it happens to be. But we got to evaluate that from 0 to L, don't we? Ugh. Okay, so I did it to myself, so we'll just do it. L plus the square root of L squared plus y squared minus y. Did I do that right? Put in 0 for x, put in 0 for x squared, and I end up with the square root of y squared. What's the square root of y squared? Y. Minus, I screwed up. Darn it, screwed up. So it's that, I didn't mind my parentheses. Minus the natural log of y. Whew. Mr. Balogh, doing bad math. Okay. And one of the things they probably beat into you in algebra class is that if you have a difference of logarithms, what can you do? You can make one go in the denominator or the other. So we'll make this look a little bit better. Natural log of L plus the square root of L squared. This doesn't look any better, Mr. Balogh. What are you talking about? Over y. There we go. A little bit more compact, at least. This is the potential of the point for this setup, right? If we change the location of this point along the y-axis, do we have to do anything different? It's just a different value of y, right? But if I now ask for the point, I don't know, along the x-axis, I'd have to go set up a new problem, because this setup wouldn't work for that. Okay, so yeah, this isn't the answer to end all answers. It works for this kind of geometry. But I just wanted to, show you that this method of integration, this method of setting up integrals, right? It's always there. It's always getting us to where we need to be, even if where we need to be looks ugly. That looks ugly, doesn't it? Natural logs and blah, blah, blahs. But the good news is, it's a number, isn't it? There's no vector directions here. And if this were a negatively charged rod, just put the negative sign in for the lambda, right? Remember that lambda is in Q. What's lambda? Q over L, right? So you substitute in the Q over L. And away you go. So let's do a ring. We're going to try and march through these pretty quick, because we've kind of been here before, right? Our difference is that instead of having to deal with vectors and keep track of vector components, this is all scalar stuff, and it's I think it's a little bit freeing, to be honest with you. So let's see here. I'll do my best to draw. This is a ring of charge. Okay. We'll put a y-axis there. We'll put sort of an x-axis. No, this is y. This is x. This would be like z. I tried to draw it in 3 dimensions. I'm not sure I'm doing any better than I did last time. Probably not. Anyway, we've been here before. Point P along the x-axis. Again, we'll set up by picking a piece of this ring, this line of charge that's been put around in a circle. I need to know the distance from there to there. If I call the distance along the x-axis x, and I call the radius of the ring a, again, don't like to use the radius of the ring as r, because I've got a different r vector, this distance vector that I've got to work with. So we'll call the radius a. So let's see, v is equal to a little piece. So the little piece is going to be k dq over r. And we've already got my dq. Why am I writing another one in there? OK, so there's my point charge formula. But now I have to I got to find r, and I got to find what dq is. push dq aside for a second. What's the length of r? If I use Pythagorean theorem, it's going to be x squared plus a squared, square root of s squared plus a squared, right? Just doing that right triangle there. So let's put that in right now, since we know it. We'll push dq off just a little bit more. X squared plus a squared. All right. What are the limits of my integration here? I got to go around the ring. So yeah, it's like 0 to 2 pi, right? Kind of going around this circle. But before I even go there, let's see if we can identify anything that's constant in this integral. What comes out? The k comes out?
Square root of x.
And the square root of x squared plus a squared comes out. Because that distance r, no matter where I am on that ring, that distance r is going to be exactly the same. So I'm not integrating over really any distance. I've got to tell my integral to go around. I could break the dq down into lambda and q's and d r's, d thetas. But really, I'm integrating from 0 to the total charge on the ring, right? If I have 10 coulombs on the ring, and I bust the ring up into 10 segments, and I add them all together, what am I going to get? 10. Right? So, the integral of dq from 0 to q, it's just q. So that means that the potential of a ring of charge on the central axis is going to be equal to kq all over square root of x squared plus a squared. I mean, I did an integral, but I didn't really do an integral. I integrated q from 0 to q. Yay! So there we go. Got a ring. What's next? Quiz! Are those the right numbers? Yeah? Okay. Moving on. Potential of a disk. So let's recycle some of what we already know. We found the, well, okay, so we'll set up again here. It's a solid disk now. We'll give it some shading here. Okay, there we go. I'm trying to get really artistic here. There's my x-axis. How are we going to cut the disk up? How did we cut the disk up before we did electric field? Do you remember? In like not like discs, they were like rings, right? They were rings, nested rings coming out. And so we're gonna like take a ring, and then we're gonna bump it out just a little bit in the radial direction of this disk. Okay, try and find out what's going on here. Okay, so my r like vector, if this is my point, right? So I know I'm going to find it by cutting up my disk into little rings. But we know that the electric field of a ring, which we just found, is kq, write the right thing, Mr. Balogh, kq, getting ahead of myself, over x squared plus a squared. That's what we got from the other slide, right? So since we already know what a ring needs to be, we don't have to go reinvent the wheel there. But I do need to modify this slightly for the parameters of my problem and the way I'm going to be integrating. If I've got a bunch of rings, which way am I integrating? Outward along the radius of the disk, right? So, let's call this distance x, and then we're going to call, dangerously, we're going to call r the radius of the disk now. And like, Mr. Balogh, you're changing the definition of r on me. Yeah. Right? And back when we did the ring, we used a. It was a constant. Nothing was happening with the ring, right? My r vector went from a point. But I don't need an r vector in here. I really don't need that line that I drew. I just need to know how to integrate across the surface of this disk. And it feels a little bit better to call that 1r. So how do I modify this equation over here to follow the symbology that I'm doing now? So this is going to be a k dq, right? And x is going to stay the same, but now I'm just going to put in r squared, right? Instead of a in my last problem. Now I'm switching symbols, making that r. Okay, so we've sorted sort of that modification of the solution I already had to fit this problem. Now I need to figure out what dq is. Can I pull the same trick I did last time where I just pulled everything out and just integrated over q and I'm done? R is changing now, right? Okay, so I can't do that trick. So that means I actually have to go find out what dq is. What unit, like which of the densities am I going to use? I can do linear, I can do surface, I can do volume. What are we working with? It's a surface. We're integrating over a surface now, aren't we? Okay. This disk has surface area. It's not like a line of charge we're going around. We're going across the surface area of the disk. We're cutting out little donuts and nesting all those donuts together. So I'm going to use sigma, which is q over a, which is the same as dq over dA, which means that dq is equal to sigma dA. And now I have to go find out what this little differential area is of my surface. So again, it's a ring that we bump outwards in the r direction. So how do I find that area? So yeah, dq is going to be sigma times 2 pi r, which is the circumference of a circle. And then how do I get an area? dr. All right, put it all together. Try to do an integral. K and then sigma 2 pi r dr all over square root of x squared plus r squared. All right, so, what are my limits? Start at the 0 and go all the way out to whatever the radius of my disk is. Constants, let's see, k, sigma 2 pi. That's all I got. 0 to r of r dr all over the square root of x squared plus r squared. That's sloppy. Oh my gosh. It's bad enough, but that was really bad. Okay. X squared plus r squared. My notes say do a u sub. So if I let u be x squared plus r squared, then what's du? It's 2r dr, isn't it? And it looks like I have a 2r dr, don't I? Right? So that means that my integral is going to have the form of a du over a u to the 1/2. And what's the integral of that? It's u to the 1/2 divided by a 1/2, isn't it? Because like u to the negative 1/2. From 0 to whatever my new limits are. So that means, right, just putting all of the form of the integral together and swapping back with my u's and stuff like that. K sigma, there's a 1/2 on the bottom, which becomes a 2. And then my u, which was x squared plus r squared. But it's u to the 1/2. So square root of x squared plus r squared. I lost a pi. Pi comes along for the ride. Sorry, being a little bit sloppy with my integration there, but made sense to me. What? Huh? What? 2x. X is a constant. Yeah. Strictly speaking, there should be partials in here, but I think I got it. The 2 on this answer right here came from that 1/2 over there, right? A 1/2 in the denominator pops back up. Because I had to use the original 2 as part of the u sub, right? Okay, so the 1/2 comes up. U to the 1/2, well, u was x squared plus r squared, so chunk that into a square root. And then all my constants were along for the ride. So that's where all that came from. But we still have to evaluate it from 0 to r. So that's 2k sigma pi, and then x squared plus big R squared minus, and then 0 goes in there, right? So it's just minus x, because square root of x, hey, there we go, yeah. So there is the potential of a disk. If you want to know the potential of a disk, anywhere on a line that's directly through its center, we're good to go. All right. How's your brain like doing? Is it remembering a little bit of this? Is there like a pale echo of kind of what we've done before? I know I went fast. I'm trying to rip the Band-Aid off really fast, right? Okay, get through the pain so that we can move on to other things, more sort of simple ways of conceiving what's going on here. But I hope that you remember, like go back, kind of compare this to the notes that you have for electric field when we did this. Because we did a point, we did a rod, we did a ring, we did a disk, okay? I'm not going to do a sphere here. The electric potential of a sphere. You know Gauss's law now. What do you suspect we're going to use for the potential of a sphere? Treat the sphere like because we're outside only. Point charge, KQ over R, we're done. Right? Okay? Potentials they're pretty straightforward. And no vector components to have to worry about. No symmetries to have to worry about. Like which ones cancels this and that and the other thing. It really is kind of a breath of fresh air. But admittedly, everything that I've just shown you is really, really useful for physicists and some electrical engineers, if you really kind of get into the gritty. But most electrical engineers are applied, meaning that they're working on circuits and power grids and things like that. And you're just really not going to need to know the potential. You want to know what happens to charges when they move through electrical circuits. And we're going to get there. But I want to bookend this to show you the power of electric potential and why we take you through this sort of physicsy way of thinking about it and doing it. Not just to reinforce all the problem solving that we had in the last unit, but to just really show you the power of the mathematical formulation that's around it. I want to return to this connection between electric potential and electric field. We've done the concept, the topographical map, the perpendicular lines and all that kind of stuff. I now want to do it from a physicist, mathy point of view. Again, just to run home how powerful some of the things you've been learning in your math classes are. By a show of hands, how many of you have finished Math 6? So, half of you, okay? A little bit more than half. If you did not raise your hand, do not panic. Okay? You are actually in a much better position than the Math 6 students at this point, because the Math 6 students are going to have to sit there and come to existential equilibrium over how much of their life was wasted in Math 6. Okay? Because there's really only one thing from Math 6 that was really, really all that important. And it was called the gradient. Math 6 students? No? Yeah? No? You refuse to remember it anymore? Okay, so those of you that didn't take Math 6, you get to watch the tears form in the eyes of those that did. Okay? But you're not required to know Math 6 for this class, but we are going to have to pull out a trick. So let me pull out a mathematical trick that's going to be really, really useful. I'll just show you how this as a person that doesn't like math, even I had to admit that this was actually pretty amazing. Okay? So here we are. We're back at that original definition of what a potential difference is, right? This electric potential being defined as follow the electric field, pull off the parts that we need. We're going to be able to find the difference if we're clever about it, right? But this tells me something. It's something that we got, that the same tricks that we were using over here. We're looking for electric potential. So what sits in front of the integral sign? A differential potential, right? So what does that mean this thing is? What's E dot ds? It's our differential potential, isn't it? We'll bring the negative sign along for the ride. Okay? So this little differential potential that we're going to try to bust up in little pieces and then integrate over, and magically it becomes the things that Mr. Balogh is going on about I don't understand. Okay? In general, there's lots of different ways we could write the electric field down. Let's just do it in Cartesian coordinates. In general, an electric field can be expressed as a magnitude of the electric field in the x direction times the x direction, right? This unit vector I hat. Same thing can be said for the y direction. And we'll go real general. Oops. Ez in the k hat. It's like this is the most generic mathematical electric field I can write down in Cartesian coordinates. I could use different coordinate systems, but we'll stick with Cartesian, okay? And those magnitudes could be positive or negative or whatever, right? And then ds, its most generic form in Cartesian coordinates would be dx I hat, dy j hat, and dz k hat. What does that say? What are like dx, dy, and dz? They're like little pieces of length in those directions, right? If I change a little distance along the x-axis, it would be dx, right? Again, reinforcing that s, in this case, this symbol s, is a generic direction. But if I want to be very specific about the coordinate system I'm in, I would break that generic arbitrary direction into different components of x, y, and z, little piece of x, y, and z, and whatever, right? Directions they happen to be. So again, I've just sort of laid out the most generic thing I can think of in a Cartesian coordinate system. All right, well, what are we supposed to do with the electric field and this differential distance vector? We're supposed to dot product them together, aren't we? Right? It's E dot ds. Well, we know something about how dot products work, don't we? If we multiply these two things together, like if there were no vector, if it wasn't a dot product and it was just multiplication, that FOIL is bad, isn't it? It's like 9 different terms because you got 3 and 3 and something like that. But what do we know about every term that's going to be like I dot j or j dot k or k dot I? If the two things are perpendicular to each other, they're all going to turn out to be what? 0. So what are the only things that survive? I dot i's, j dot j's, and k dot k's, right? Everything else disappears, which means that my differential potential, okay, nice sign comes along for the ride, ends up being ex times dx. And I dot I is just 1. Plus ey dy plus ez dz. It just literally just pulls out those singular pieces that are all consistent with each other as, this hopefully isn't that much of a surprise, right? I haven't done anything real surprising yet. I've just done a dot product, okay? So I can now find the magnitudes of the components of each of my directions. In other words, if I just look at ex alone, all by itself, I can pull off what ex is. What's ex going to be? Negative dv dx. It's a change in potential divided by the change in the x direction, giving the electric field in the x direction. Mechanically, though, so that was the idea, but mechanically, what is that? Calculus-wise? It's a derivative. So if I want to find the value, the magnitude of the electric field in the x direction, I take my potential function, whatever it is, and do dx, and I can find the x component? Yes! How do I find the y component? Ey is going to be negative dv dy. And the z component? dz. This is fantastic! Because the potential is a scalar, isn't it? But I can go back and find the individual components of the electric field, this vector thing, even though I start with a number, like scalar function? Yes! The answer is yes. This is great. Because I can do an end run around some integrals this way. So we can formalize this just a bit. The vector electric field, okay, in Cartesian coordinates would be negative. And negative is always along annoyingly for the ride. I hat dv dx plus j hat dv dy plus k hat dv dz. I've literally taken, like, this is my ex, right? And I'm rewriting putting in, right, my ex. Take my ey, put it in there for ey, put it in there for z, okay? I just rewrote my electric field in terms of these derivatives, okay? And to compress this even more, to make it so that I don't necessarily have to keep writing out all of those different derivatives, there's a symbol that we can swap, okay? And the symbol that we're going to use, is an upside down triangle. The upside down delta. It's called the del operator. Okay? And it is a vector operator. Okay? Where this del operating on a function, the operator always has to operate on a function, is defined as very special, weird-looking derivative symbols times the vector directions. The del carries the vector directions for us. And as long as we do these derivatives of each individual directions correctly, we'll be okay. Why did I write really funky d's?
When you multiply
That is not equal to that. Did they teach you this in Math 6? What's this? A derivative. What's this? A partial derivative. Okay. What's a partial derivative? Quite frankly, they are the best derivatives in the universe. Partial derivatives are basically how the universe is put together. Most of the time, the universe is doing partial derivatives, not this kind of derivative. Okay? A partial derivative, and you see this symbol, and you're doing a derivative with respect to x, anything that is not an x is constant over that integral. So if I take the partial derivative of x squared plus 3y cubed, what is the answer? 2x. What happened to the y cubed? It's with this symbol, anything that's not an x is a constant. What's the derivative of a constant? Because if it were the other kind of derivative, well, now we're into, it's like chain rule, and we'd have to say dy dx, like if y had some sort of functional thing to do with that. Like, it gets really, mathematicians get all bent out of shape if you don't do it, but like the universe uses partials most of the time for everything, okay? What if this were the partial with respect to y? What would the answer be? 9y squared. Where'd the x squared go? 0. And if this were that? 0. Partial derivatives are amazing, okay? And the del operator, okay, is a set of partial derivatives. So when you take the derivative of the potential function with respect to x, and there's a bunch of y's and z's in it, what do? Treat them as constants. Makes the derivatives much easier. Okay? So, and just a little bit of insight here. If we move outside of Cartesian coordinates and we go to spherical coordinates, okay, ER would be negative dv dr in the r hat direction. We only do that. We don't do theta and phi in spherical coordinates because that one can get a little bit hairy, okay? But if we know what our potential function is, we can find the electric field. And I'm going to do that right now. I'm going to show you an example of doing this. But what we've done here is this isn't magic. We just looked at our integral and said, I know what my differential is, and if I think carefully about what that differential is doing, I can actually connect that differential potential back to the electric fields that I am trying to find. So, doing that, let's do, that's being conductors. Let's do, yeah, there we go. Okay, let's do the ring. Let's do the ring. We just did the ring today, right? So we know the answer for what the potential is for a ring. I can't spell. Can't write either. Ring. The ring potential was kq all over the square root of x squared plus a squared. We had set it up before, right? We already know what the answer is for what the electric field of a ring is. Back in chapter 22, okay? We got that answer, so we can go back and compare, okay? But we're going to find the electric field by using our newfound magical del operator thing, okay? We know something about, we really do have to be careful now because we're introducing vectors back into the situation. But what do we know for a ring, and we're finding the electric field there at point P. What do we know about all the other axes other than the x-axis direction? The electric field vectors at point P, which way are they going to be pointing only? In the x direction, right? All the other directions around it will cancel each other out. I mean, we could get electric, like from the top, we could get electric field pointing down. From the bottom, we get it pointing up. But those are all going to cancel each other. And the only things we're going to have are the ones that are pointing along the x-axis. So by symmetry, I can ignore, okay, you know what, I'll do mathematically too. But by symmetry, I know that all I'm going to get is an EX. And that EX is going to be minus the partial derivative with respect to x of my potential function. So that is the partial derivative of kq times x squared plus a squared to the negative 1/2. I just kind of pulled it up out of there, right? What's the derivative of that thing? Oops. Negative kq comes out. The derivative of x squared plus a squared to the 1/2. it's going to be the thingy, right? And we subtract more off the top, right? So we subtract 1, so we get negative 3 halves. And then after the thingy, you got to remember to do the derivative of what's inside. And so what's the partial derivative of x squared plus a squared? It's just 2x. I followed all my derivative rules there, right? Okay. And, I didn't bring down a negative 1/2, right? Because the derivative is you take the thing, you bring it down, you subtract 1, you do, right? Okay, got it. So negative signs cancel. I've got a 2. Let's see, I've got a, no, the 2's cancel. I better keep track of some of this. The 2's cancel. The positive signs cancel. Yeah, that's you. So we've got KQX all over x squared plus a squared to the 3 halves. I hat. Isn't that what we got before? For the electric field of a ring? You can go check your notes, but that's what we got before. And I don't know about you, but I always liked derivatives more than I liked integrals as far as turning the crank. Mathematically, even without the symmetry argument, what would the EY component look like? Partial derivative with respect to y of negative KQ all over x squared plus y squared to the 1/2. Could have written it the other way. We have to do the regular derivative, right? KQ negative 1/2 x squared plus y squared to the negative 3 halves, and now we have to do the integral, the derivative of the inside. Y in this problem is a constant, right? Anyway, the A is a constant. So what is the partial derivative with respect to y of x squared? 0. Of a squared? 0. Wipes it out. What happens when we do the partial with respect to z? Are there any z's in there? No. So what's it going to be? When a physicist has to find an electric field, we'll go find the potential first. Potential's easier to find. I don't have to worry about vector directions. And then I just whip out a del operator, and I've got my electric field. So for those of you that, you don't have to admit it publicly, like mathematics, can see the beauty of it, okay, and its power and potential. I mean, it's just so, oh, pun intended. It's so good. Like some of these mathematical connections back and forth. And that del operator with a dot product is called, I think, isn't it called the divergence of a function? And then we're going to do one later where there's a cross product in it. And that would be the curl of a function. Basically, we're asking how much does something spread out? And for electric fields around point charges, do they spread out? Yeah. Right? And so this function captures that idea perfectly. Curl has everything to do with how things rotate. And we're going to have rotation of fields when we get to magnetic fields. So the cross products will come at us. But anyway, it's one of the few times I just sit back and go, oh, that's cool. Okay. Linking this back to our conductors. Remember electric field and conductors? Right? What's the electric field inside of a conductor? 0. Always 0, right? So if we have our conductor, did I put any pictures for this one? Of course I didn't. Okay. So let's take, I don't know, lump O metal, right? we know that if we dumped charge on this thing, it would all go to the outside, right? Because conductors allow charge to go through them, so it'll spread out as far as they can go. We know that the electric field inside will be 0. But what is the potential on this conductor? If the electric field inside the conductor is 0, then what's the potential? Don't know. You all said 0, but it could be not 0. It could be anything. More important than what the actual potential is, because that'll depend on several factors. More important is if we go from, say, one point, like that point right there, to this point over here, what will the delta V, the change in potential, be? 0. So electric fields being 0 inside conductors guarantees that inside that conductor the potential difference is 0, but that does not mean the potential is 0. It means that the potential is the same everywhere on that conductor. So, when you are trying to explain to the police officer that the electrical pole jumped in front of your car, officer, I have no idea. I was just driving down the road and the electrical pole jumped in front of my car. Okay? And you're sitting there and the electrical wire is draped across your car. What should you not do? You can touch the surface of the car all you like. Why can you touch the surface? So your car is now at 20 to 25,000 volts of electric potential with respect to the ground, because that's what's in a pole with the wire, the electrical wires on it. So why are you safe in the car even though your car is at 20,000 volts? The difference in potential between any 2 points on your car is what? 0. 20,000 minus 20,000. And so will there be any electrical potential energy between those 2 points? No. And with no electrical potential energy, no work can be done. So you're safe. But what happens if you try to get out of your car before PG&E shows up? If you're touching your car at 20,000 volts and you step to the ground, what is now the potential difference through you? 20,000 volts. Why is it that birds can land on high voltage power lines? They land 1 foot on the wire, 1 foot on the wire. What is the electric potential between their legs? 0. Even though it's a 20 to 25,000 volt line? Yes, it's 0. And so the birds are safe. When are birds not safe on an electrical wire? When they're too big. Okay? My grandfather retired and became a farmer. He was an industrial chemist, retired, became a farmer. Was a farmer longer than he was an industrial chemist. So my grandfather, I guess, was a farmer. He had electrical lines that would go out to some of the parts of the field to run some of the valves. And every so often we'd go out and we would find an owl dead on the ground. Owls are big birds, okay? And they have wingspans, okay, that are pretty big. So owls would come into land and flap their wings in that flare to come down to a stop. And their wings would touch 2 different wires that were going out there. One's 20,000 volts, one's the ground return. Okay? And now the owl has 20,000 volts across it, and you have a dead owl. Little tiny sparrow doesn't have the wingspan to reach across, right? So, gotta be careful, right? If you're a big bird.
Then in the 1980s, helicopters and barehanding combined for a remarkable new way to maintain live lines. With this technique, the lineman and the helicopter are both energized to the line voltage. And again, they are safe because they are not touching a path to the ground.
Safe is a relative term here.
Helicopter line crews can work much faster than traditional teams on extreme high voltage transmission lines. Linemen equipped with bucket trucks and hot sticks can replace about 8 line spacers in a day. During the same time, a skilled helicopter team of linemen and pilot can replace over 200.
In my career, I would never have dreamed that I would see a helicopter doing power line work. I would think it's a little scary the first time you do it too. You sit
Yeah.
there on a platform on the side of a helicopter and you fly right next to a wire, and you're hoping that the propellers don't get tangled up in anything. And some of these pilots, I have to commend them. They can hold that helicopter in the same place the longest of anything I've ever observed. These guys are extremely good at what they do, and I commend them. They do a good job. They're safe. About the only time they ever have anything happen is when they have an equipment failure.
Line maintenance with helicopters is expensive, and there have been fatalities. But today, linemen and pilots train for 2 years to master the technique, which is considered safe under the right conditions. However, no safety tools, procedures, or regulations are effective if a lineman loses his focus and concentration.
What did we just see? Did you see the pokey? The lineman had the pokey. What was he doing with the pokey? Making sure that by the time he touches that line, that the helicopter and line are what? The same potential. So they can climb out on that line, do whatever work they need to do, right? Helicopter goes off and does something, has lunch, I don't know, comes back, right? Okay? Helicopter's blades going through the air, lots of static electricity, definitely a different potential than what the line is. So pokey out, right? Discharge, discharge, discharge until they meet. Now everybody's at the same, and things are perfectly safe. But falling. So, I mean, these are the kinds of heroes that make our modern life possible. Good friend of mine is one of these. I used to dangle underneath helicopters to fix high voltage line. I was like, Clint, you're insane. Back when they first started doing this, the linemen involved complained of nausea and headaches. And you're kind of like, well, duh, you're dangling off of a helicopter, right, hundreds of feet off the ground. They're like, no. It has nothing to do with like vertigo. Like they literally were kind of just getting sick. And it wasn't motion sickness, and it wasn't. Turns out that the electric field around the lines was so high that it was affecting blood flow to their brains. Because there's ions in the blood, iron and other things, right? Okay. And so blood flow was being constricted or pooling up or doing weird things. And so did you notice what everybody was wearing? They had a helmet, but they also had a suit. That suit isn't a flight suit. It's impregnated with metallic threads. What are they wearing? Faraday cages, okay? And they don't have to enclose the face. Just turns out if you wrap the head and wrap the rest of the body, the trunk of the body, all of that problem went away because they were inside of a conducting mesh to keep them safe. That was the end of chapter whatever, 24. And we will do probably 25 in one day. 25 and 26 maybe in one day. They should be the same chapter, but we'll see how far we get on Wednesday. See you tomorrow for the exam autopsy.